Okay, good to go. Okay, I'm Nicholas. I've been a RxJS core team member for about 2 years. I've been using RxJS for probably about 5 years. I'm on a break at the moment, working on some of my own secret squirrel projects.
Hi, and I'm Moshe. I am also on the Rx core team. I've been there for a little under a year. I'm a senior software engineer at Bloomberg.
Cool. So our talk is about automated analysis for RxJS programs. It's a bit vague. So what we mean by automated analysis is identifying unexpected situations based upon known behaviors of sources and operators. Basically, whenever you're writing RxJS code, if you do something that's likely to be surprising, we want to be able to give you feedback straight away. So in this talk, we're going to present a proof of concept solution that we've put together that uses the established guarantees and behaviors that come from the docs to provide you with immediate feedback when you're writing RxJS code. So we'll look at how the solution works, and then we'll show you the sort of feedback that it's able to give you. And we'll start by looking at a scenario. So in this scenario, we are relatively new to RxJS, working in a team, and we've been given a bug to solve. So the problem is part of our application has just stopped working. It's one of those really fun bugs where you don't get an error, you just get nothing. So we spend a bit of time looking at it, and we narrow it down to this bit of code. So it's doing a fork join, it's getting some authors, it's getting some books, and it's joining together. Being fairly new to RxJS, we're not super familiar with fork join, but we're pretty comfortable. We've done a good bit of work to narrow it down to this part of the code that's causing the problem by not doing anything. So we take this to the senior developer to get her input. And she looks at it, and she's familiar with RxJS, and she gives us 2 comments. And we can take those 2 comments, and we can go away and look at a couple of other things and then figure out where the problem actually is. And she's able to do this because she's got just a lot of absorbed knowledge. She's read the docs, she's worked with it for a long time, and she's just has all this stuff in her head. Now, what we want to be able to do is use that information in our tool to give feedback to the person who's actually doing the RxJS development. So the way we're going to do that is by using types. Now, this is not a new thing. There are other Rx implementations that use types to describe particular behaviors. In Rx Java, there are a whole bunch of particular classes that are used in particular situations. So there's a single, there's a maybe, there's a connectable, I think. But we'll look at the single because there have been a few issues raised in the RxJS repo with people asking for a single. Can we have a single so that when we're looking at our code, we can see that this thing is just going to emit once and then that's it? Well, it's a little bit weirder than you might think because the single that's in Rx Java, it doesn't complete. It either emits a value or an error, and that's it. There's no complete signal. So things get a little bit strange. And they get even stranger when you look at its observer. Single has a specific observer for the single instances. It doesn't have an on next notification, and it doesn't have an on complete notification. It has an on success notification and an on error notification. So it's weird because it doesn't have the same notifications that observable does in RxJava. So if we were to take this concept of introducing a different type, different class like single into RxJS, our API would get even bigger because our operators would have to deal with singles as well as operators. And on top of that, it works quite differently in Java because Java has a nominal type system, whereas TypeScript is structural. If 2 things have the same shape, they're the same type. So rather than looking at adding classes to do this, we've taken the approach of adding trays. We're going to add some traits to the observable type. And what we're going to do is literally add it to the observable type. So observable at the moment has 1 type parameter. It has the element as the type parameter. So observable of string is going to emit string values. So we've added another type parameter that's only used inside the type. So these traits aren't used anywhere else. They disappear once it's compiled. They're a type type space thing only. They don't exist in the value space. So we've added the traits to the observable. Now, the default traits, they look like this. So it's got a bunch of properties in it. It will tell us whether or not it's asynchronous, whether or not it completes, and it gives us some idea of how many elements an observable is going to emit. Now, these are the default traits. They don't actually give us any specific information because the types are very broad. So async as a Boolean could be true or false. What happens with our proof of concept is that we provide narrower traits from observable sources. So if we look at from fetch, the traits that go into the observable that's returned will say that it's asynchronous, it's going to complete if it doesn't error, and it's only ever going to emit a single response. So this gives us all the things that we need to understand what it is that we're getting from fetch. So we get some traits from our source, but those, anytime you're using RxJS, you'll be using operators. So those traits are going to flow through operators. So the operators themselves will take the traits from the source, they will manipulate those traits, and you'll potentially get an observable that comes out the other end, which has different traits. So if I add some explicit types to this just to show what's happening, we can see that in our source, we've got these traits. It's not asynchronous, it will complete, and it's always going to emit 3 strings. Now, if we run that through a take 1, and I add the explicit types just to show you what's going to come out of the take, we can see that the async hasn't changed, it still completes, but it's only ever going to give us a single string now because we've done a take 1 on it. Similarly, if we've got a source and we apply a delay to it, the way the traits flow through this composition is the only thing that changes is the asynchronicity. So it's always still going to emit three strings, but it's going to emit those asynchronously. So the way this works is it's all done inside TypeScript. Inside of each operator, there is some type level programming that manipulates the traits in the observable that serve as the source to give us the traits for the observable that's coming out of the operator. So I'll hand over to Moshe now, and he can tell you a little bit about type level programming.
Thanks, Nicholas. Yeah, so type level programming is the act of using the TypeScript as a way to program on the type level thing. So to bring that into a more concrete example, let's go through a simple proof of concept for that. So we're going to create a class, an interface, and the interface is going to be a box interface. And this is, if you squint, you could pretend this is an observable, and T is, it's generic over T, and T is an array-ish type, or it could be a tuple type. It basically means many values of T. So this is very close to array, and what we're going to do is we're going to expose a single method on it, and that method is going to be take. And this is going to be similar to the take operator in RxJS. And you could take n number of elements from the box. So if you have a box of 100 numbers and you take 3 numbers from it, you're going to get 3 numbers. So think like that, and the return type is going to be a box of T as well. So if we look, what we're doing is we're saying take is a number, but that is a little bit broader than we need it to be. And what we could do is we could create this magic type that's going to limit what you could do with it. So we're only going to let you take less than whatever T is. And this is going to be, this is going to change based on the generic of the box. So how does this work? So this is we're going to look at take less. So take less is, this is the type level programming idea. And what we're doing is we're inspecting some more concrete thing of a tuple, and we're going to do things based on different conditions that that tuple has. So over here, what we're doing is we're taking a T, which is, we're just calling it an array or tuple. And what we're going to do is we're going to inspect the length property. And this is available on the TypeScript level. So this isn't actually a value. This is a type information thing. And we're using conditional types, and type level programming is just like conditional types galore all over the place. So what we do over here is we see if the array is an empty array, then the take less type is going to quote unquote return the number 0. And similarly, if the tuple has a length of 1, then the return value for take less is going to be the union of 0 or 1. And similarly, if it's 2, you can return 0, 1, or 2. And if it's 3, you can return 0, 1, 2, or 3, and so on. And technically, we could abstract this to not be drawn out like this, and to have 20 lines of code similar to this and retyping it. But in actuality, a lot of TypeScript code, especially library code, is written similar to this, where you have overloads that are extremely wordy and lengthy. And if you look at lib.t.ts in the TypeScript source repo, you're going to see this pattern pretty often as well, not specifically in this case. Okay, so let's actually use our box and see what we just got from that. So over here, we're creating a factory function, and all this does is this just takes a number of arguments and it turns it into a box. And we're going to return the take, and the take, we're just going to use the array.slice because it serves our purpose of taking n number of elements. And now let's look at actually using the box. So over here, we're going to create a box of an empty box, right? So if we do next, yeah. So if we go over here, we're creating a box. We're not giving it any arguments. So that means the rest argument in the ... t and above is going to be an empty array. So, and that's reflected on the type information of that box. So it is an empty tuple. So right now, if we were to call b0.take0, that would be fine. However, the interesting thing happens when we try to do something that we shouldn't be doing. So if we call b0.take1, what's going to happen is TypeScript's going to know that a box of size 0 matches the first line of that type of that take less type, and it only allows you to pass in a 0. It does not allow you to pass 1, and it's going to complain and say you actually can't do that, which is catching a potential error of the user and letting him know that, hey, what you're doing is probably wrong. And similarly, if we were to try other cases, if we were to have a box of a single element and we could take 0 or 1, but if we try to take 2, it's going to complain. And similarly, if we have a box of 2 elements, we could take 0, 1, or 2, but we can't take 3. And again, we could generalize this using some more fancy type magic and to not have to draw out all these cases. And it'll work to a very large number before TypeScript stops trying to do type level programming for us. Okay, so going back up, the problem with this is that this is very restrictive because sometimes you do want to take more elements because you don't want to have to care about the size of the array when you're taking something. You always want to take, you have a list of unknown amount of numbers, and you only want to take the first 100 for pagination purposes. And sometimes that number is known at compile time to be 50, and then the compiler is going to complain at you, and that's a little bit too aggressive. And in fact, the array.slice method doesn't complain if you try to take 100 elements from an array of 3 elements. So this is, it doesn't really match our expectations of what we should be getting alerted to. So what we're going to do is we're going to remove the constraint of n to be only take less than t, and we're going to turn it back to number. And then we don't need that type helper anymore, and that gets rid of some of the complexity that we need. So now this code is pretty much what we would have written initially. But if we look, we're going to see something interesting, and that is when we get to the last line, the empty box, take 1. TypeScript knows a lot of information about that. So it knows that this is an empty box, and it knows the method you're calling at it is a take on an empty box. And at a compile time, when TypeScript is morphing this code to JavaScript, it knows that n is the constant 1. Or if you pass in a variable that has a constant value of 1, it'll know that as well. And it's very smart about this. And that information, that type of information is retained and able to be passed on to other tools in the pipeline. And so there's still some more optimizations that could happen. So right now, what you're seeing is all the type information just go and everything magically happening. But there's other points to highlight over here. And that is, if I have a box of 5 elements and I take 3 elements, the returned box should only be a box of those first 3 elements. And that's also going to be type information that we would do something very similar to take less, and we would have like a take operator, a take type, and that would slice the array in the type level in the TypeScript type helper, and that would return that. And that would also get added to this complex pipeline of what we're trying to accomplish. So to talk more about what goes on further down the pipe, I'm going to pass it back over to Nicholas.
Thanks, Moshe. So with the type level programming that happens in TypeScript, what we have going into each operator are some traits, and coming out of each operator are some traits. And what we want to do is look at those traits and at the known behavior of the operator and let the developer know if something unexpected is likely to happen. So we're going to use the linter to do this. And to show you how the linter works, we'll have a look at this expression. So it's just going to call take 5 on an observable. It's never going to emit and subscribe to it and try to write it as a console log. So nothing's going to happen, but it gives us an example we can work with. So the linter, ESLint, deals with the source code as an abstract syntax tree, an AST. And this expression that we've got is a call expression. It's calling subscribe and it's passing console log. So the tree is built by breaking this expression down. The call expression breaks down into a callee, the thing that's being called, and the argument that's being passed. Both of those are member expressions. So subscribe is a property on the observable that's being returned by take, and log is a property on console. So both of those expressions break down into additional nodes. Of those, we've got a call expression, which is the pipe call on never, which breaks further down into the callee and the argument being the take call, callee being the pipe method. And that breaks down, and the call expression for the argument breaks down. So now it's completely broken down, and we can see the nodes that we're interested in, the nodes that have traits. We've got the never, which is the source. Some traits come through there. They flow through the take. That creates some new traits. Then they're consumed when the subscribe actually happens, because the subscribe is made on an observable, and that observable has traits. So usually when you're looking at ASTs, you're thinking about what you would have to do to find these nodes. Now, the really nice thing about ESLint is that you don't have to walk the AST. Each ESLint rule works by returning a map of listeners, excuse me, to ESLint, and those listeners have keys that are very much like CSS selectors. So to be notified of any time we find there's a take operator in the source code, what we need to do is add an entry to our map of listeners where we want to find call expressions, and we want to further qualify that by saying we want call expressions where the callee is take. Now, when this rule runs on the source code, this listener will be invoked anytime a take operator is used. Similarly, if we want to catch the subscribe calls, we want call expressions, but we only want the call expressions where the callee is a member expression and the property is subscribe. So whenever we're calling the subscribe method. So we can fill this out, we can add these listeners, and then we can add some analysis. We'll have a quick look at what the analysis looks like. The core bit is in ESLint, we have two sort of realms. Files are linted individually on a file by file basis, but TypeScript, when it's built using the type information, it needs to build the whole program. It needs information from various files. It needs information from stuff that's in node modules. It needs to find all of the types so that it can verify whether or not a particular file has any problems with those types. So TypeScript has a program, and that program has a type checker. And to move between these realms, this realm of the syntax that's in this source code file that is in the AST, we have from the TypeScript parser a map that will map ES nodes to TypeScript nodes. So obtaining the TypeScript node from the node that was passed to the listener is as straightforward as going to the map and passing in the node we received and then getting the TypeScript node. So this function that I'm calling here, get operator traits, gets the input traits that are flowing into the operator and the traits that are flowing out of the operator, so we can do some checks on those. Now, those traits are obtained by first getting the type from the node. So we pass our TypeScript node to the type checker and say, please give me the type at this location. Now, what this type is this is a type, think of it as a type descriptor. It's an object that has all sorts of information about the type that's associated with that node. So it'll have a name. That name in this case will be observable. I mentioned earlier that observable in our proof of concept has two type parameters. It has the element type, observable of string, and it also has the traits. So we can get the traits from our type descriptor by looking at the type arguments and saying, give me the second one of those, the second one in the array. And that's our traits type. So the trait types the descriptors are describing types that look like this. This is what they would look like in the program. The first one is just the literal type that would be associated with the never source. It's not asynchronous, doesn't complete, and it doesn't emit any values. But things get a little bit trickier when we look at what the type is that's associated with the observable that's returned from the take operator. It's a take type. So it's a take type that's taking the input traits, and they'll be the traits that came from never. And looking at this, the first thing is, how do we figure out whether or not any of these properties have changed? Because if we were to look at, say, the max property inside of this type, we would find one of the complicated conditional types that Moshe was talking about in the type level programming, because the take type here is the type that encompasses all of the type level programming that's manipulating the input traits, which is a worry, because what we want are the actual properties. Well, fortunately, the magic type checker has a get properties of type function. So we can pass in our trays type and it will resolve it. You can think of it as squashing it. It works out all the conditional types and gives us the actual resolved async, completes, min, and max. And from those, we can compile, we can just generate an object that we can use to describe the input traits and the output traits. So in this case, they're the same because the take wasn't able to take anything and the max stayed at 0. And the object that we're using here, we don't worry about the types of the min and the max, we're only worried about the numbers. So we take these and then run those through our checks. So we're going to check the completes, we're going to check the length, where the length is also passing in the argument that was passed to the take operator. And we can see that there are a couple of things that are probably worth warning the user of this take operator. The first one is obvious. The first one is that they're trying to take 5 and there's nothing available. So we should tell them about that. The second one is a little bit more subtle. Because they've asked for 5 and the source doesn't have any elements, it's not going to complete. Now, a lot of times people use a take operator, they're expecting it to take this thing and then complete the source, and that's going to trigger, the unsubscription and all sorts of other things. But if it doesn't have the elements there to take, it's not going to complete, and that could affect some other unusual behaviors if you're expecting the take to affect an unsubscription. So the rules that we have for this take operator will affect 2 warnings when it's used in that context. It will say fewer elements than specified will be taken, and also the observable will not complete. But it doesn't stop there. There's a little bit more that we can do, because there's a subscription made. Subscribe was called on this composed observables, and the traits will flow all the way down to the subscribe. And when subscribe was called, it passed in console.log. So they've passed, the person who has written this code has passed in a next handler, console.log. But we know that no elements are going to be admitted. So we can affect another warning. We can say the next handler that was passed is not going to be called because the subscribed observable isn't going to next. It's not going to emit any values. And we can take this further, because if we'd passed in a complete handler, and we can tell from the traits that were on the observable that was subscribed to that it's not going to complete, we can affect another warning. We can say the complete handler that you passed here, it's just not going to be called. We can guarantee that it's not going to be called because the type level programming we've done with the traits tell us that it can't complete. So we can convey this information immediately to the person who's written the code without them even having to run the program to see that the handlers that they put in aren't going to be called because there's something else happening further up the composed pipeline. So coming back to our scenario, what our senior developer would have told us when she looked at fork join is that if fork join isn't doing anything, then at least one of the observables that's being passed into it is either not emitting a value or it's not completing. So in our scenario, we went off and we had a look at authors and we had a look at books and tried to figure out which of these was either not completing or not emitting a value. With our proof of concept tooling here, we'll get a warning straight away because it'll say fork join won't emit a result because the author's source won't complete. If the type level programming is able to figure out that that source can't complete, our rule will be able to affect a warning straight away. Now, we think this is pretty cool, largely because it just leverages so much from TypeScript and so much from ESLint. TypeScript just does so much work to compose all of these traits as they flow through the observables. And ESLint makes it quite easy to grab the nodes that we're interested in and pluck out the traits that either relate to an observable or relate to the inputs and the outputs of an operator. So we think it's pretty cool. I also think it's pretty cool the way that all of this information exists only in the type space and it just disappears. So there's no runtime overhead for this sort of analysis. It disappears once it's compiled. So the question is, what happens with this now? I think we've got a bunch of other higher priority items in RxJS at the moment. We need to finish the work that Ben's putting into reducing the size of all the operators. We need to also look at moving the types to modernize them so that we can use TypeScript 4 to reduce the sheer number of overload signatures that we have in the library. And the other thing that we can do is we can have a closer look at the type level programming, as Moshe suggested, that's in the traits solution that we've proofed out here, to take advantage of what's coming in TypeScript 4.1, because there are some things in there that are really cool that we can take advantage of. So that's just about it. There's just one more thing that I would like to do, and that's thank Moshe for the PR that he put together so many months ago that really started us on this work. So thanks, Moshe, for that. And thanks to everybody else for listening to our talk.
Thanks.